Right now, there are tens of thousands of active, human-made machines orbiting above our heads in the vacuum of space. These artificial satellites are strictly purposed constructs. They are dense packages of specialized electronics, sensors, and power systems designed to operate continuously in an entirely frictionless, hostile environment. This technical illustration highlights four primary satellite categories. Communication and navigation models form the hidden backbone of our daily infrastructure. They handle the routing of global internet traffic and provide the precise geospatial timing required by modern financial systems. By contrast, Earth observation weather systems and deep space scientific probes are built to look outward and downward. They utilize highly calibrated parabolic dishes and sensor arrays to gather high-fidelity data regarding atmospheric shifts and distant cosmic phenomena. But an engineer cannot simply build a sensor package and launch it into the void. A satellite's physical form and daily function are dictated entirely by its specific orbital mechanics. Orbit classifications define strict engineering compromises. The altitude and shape of the path dictate exactly how much of the Earth the satellite can see, how quickly its signal reaches the ground, and the resolution of the data it can collect. To understand how aerospace engineers design these multi-million-dollar platforms, we first have to master the strict physical laws governing the tracks they run on. Look at this 2D grid. Orbits rely on a counterbalance between forward velocity and inward gravity. This creates a geometry governed by Kepler's first law, locking the object into an ellipse. Gravity anchors the planet to one focal point, resulting in an asymmetrical loop. Engineers can manipulate the eccentricity, the exact amount of stretch in that ellipse, by carefully altering the initial launch velocity of the spacecraft. A satellite is a projectile moving forward so fast that as it falls, the Earth's curvature drops away at the exact same rate. Moving to a 3D model, we can map the specific altitude bands engineers use. This glowing blue ring is low Earth orbit, or LEO, spanning from 160 to 2,000 kilometers above the surface. Machines in this inner band travel at massive speeds, completing a revolution every 90 minutes. This proximity allows detailed optical imagery and signals bounce with near-zero latency. But that low altitude creates a limitation. LEO satellites cover only a tiny, narrow swath of the planet. To solve that geometry problem and achieve continuous global coverage, engineers deploy massive, overlapping constellations, like the thousands of individual units making up the Starlink network. Further out, between 2,000 and 35,786 kilometers, we find medium Earth orbit, or MEO. This middle volume optimizes global navigation systems like GPS. MEO perfectly balances competing variables, maintaining low latency while projecting a wide coverage footprint to map the globe. Pushing to the absolute limit, a massive red ring marks geostationary Earth orbit, 35,786 kilometers above the equator. At this altitude, orbital mechanics create a unique synchronization. The satellite's orbital period matches the Earth's rotation, effectively freezing the machine over a single geographic location. A single geosatellite can broadcast to an entire third of the planet. The trade-off is extreme distance. The signal travels so far it incurs a 240 millisecond delay, limiting its use for real-time interaction. Standard circular orbits force a direct choice. You optimize the speed of data transfer or the size of the coverage footprint. You cannot have both. Standard circular orbits cannot effectively see polar regions, so engineers use highly elliptical orbits. This creates two extremes, the perigee close to Earth and apogee far out. To sweep equal areas in equal times, the satellite accelerates violently past perigee, then slows toward the apogee. This velocity drop creates an intentional dwell time. The machine effectively hovers over a northern polar region, ensuring long, continuous communication windows for extreme latitudes. We apply a different manipulation for imaging, utilizing a sun-synchronous orbit. Relying on orbital precession, engineers calculate the trajectory so the orbital plane rotates exactly 1 degree per day, perfectly matching the Earth's movement around the Sun. Because the angle to the incoming sunlight never changes, the satellite passes its targets at the exact same time daily. The shadows are identical, allowing computers to track minute physical changes on the ground over time. Orbits are highly adaptable geometric tools. Engineers actively warp the math to bypass the physical limits of geography and lighting. Once injected into these perfect mathematical trajectories, the machines do not coast peacefully. The vacuum of space is highly disruptive. Look at the actual forces at play here. The Earth is not a perfect sphere. Its lumpy mass distribution generates geopotential anomalies, uneven pockets of gravity that constantly drag satellites off their paths. The massive solar arrays, battery banks, and complex thermal radiators exist solely to keep the central computer alive long enough to fight these anomalies. That fight is handled by the attitude and orbit control system. This is the active defense mechanism guarding against orbital decay. Using continuous data from onboard sensors, this system spins heavy reaction wheels and fires physical thrusters to execute precise station-keeping maneuvers, forcing the hardware back. A satellite is a survival engine. It burns through its limited fuel reserves every day just to protect its precise Keplerian geometry. When we view this complete architecture simultaneously, the dense, low-altitude swarms of LEO, the highly organized navigational rings of MEO, and the massive locked anchors of GEO all function as a single synchronized machine. Altitude dictates latency. Eccentricity dictates dwell time. Inclination dictates the coverage area. Aerospace engineering is a harsh optimization problem. You balance those three specific variables against the physical limits of gravity and rocket propulsion. The precise execution of that math is what allows a farmer to run precision agriculture equipment, directs a Coast Guard helicopter to a distress signal in the open ocean, and timestamps billions of dollars in automated financial trades down to the microsecond. These machines operate in total silence, millions of meters above the surface, but they function as the invisible structural threads actively binding modern civilization together.